So I'm Robert Neal. I'm a software engineer at Twitter. Today I'm going to be talking about a personal project that I've been working on, which is a reinforcement learning library in Scala 3, and to talk about an implementation of that using that library. My daughter Erin will be speaking as well.
Hi, I'm Erin Neal. I'm a freshman at High School in San Francisco.
Cool. So first, let me set up this library. So to be clear, this library isn't a library that's meant to be put into production and scale. It's really a library for testing algorithms and learning algorithms. And to help understand what I mean there, I'll talk a little bit about the motivation. So the motivation is twofold. So one motivator was a reinforcement learning reading group that we did at Twitter last year. So like many reading groups, each week a different person would sort of dive into the details of the book we were reading and put together some sort of a summary and talk about the details of that week's reading. But inevitably what would happen, and this happens in a lot of reading groups, is the other people in the reading group would have other things that they're responsible for. They'd get distracted. They wouldn't be able to dive in as deep as the presenter. And so one thing that I found that works really well in reading groups, whether they're machine learning reading groups or category theory reading groups, is having everybody in the reading group implement the week's reading. And one way that would facilitate that is if you had a library for doing so, for reinforcement learning. So that was one of the motivators. Another motivator was a talk that we had last year from an intern who was working on reinforcement learning for their PhD and had written this paper with a novel algorithm for reinforcement learning. And one of the things that you see when you're reading papers in reinforcement learning is that these new algorithms are often written because an older algorithm doesn't work well in a particular scenario. So when you see the simulations that show that this algorithm is better, it's better for the particular scenario that the paper is writing about. But you might want your own test bed to test whether or not it works well in your scenario, or just to understand how the parameters affect it in different scenarios. So those are sort of motivations for creating this reinforcement learning library. And so next I'll talk a little bit about what reinforcement learning is for those of you who are less familiar. So reinforcement learning is really one of three categories of machine learning. So there's supervised learning, unsupervised learning, and reinforcement learning. And if you're familiar with machine learning, you're most likely most familiar with supervised learning. And supervised learning typically is the case where you have some model, you train it on some data, and once you get the model that you like, you put it into production, and it gives you some deterministic predictions for some input. So you might have, for example, a model that predicts whether or not somebody's going to click on a button in a conversion funnel. And so for that particular user, you might predict, say, with 0.7 probability, they're going to click on this button. So you show them the button. And it might turn out that they don't click on the button. But next week, when somebody else comes with similar user features, you still get a 0.7 probability that they're going to click on the button. Reinforcement learning, one of the ways in which it's different is that it's learning as it goes. So if it decides to show a button to a person and that person doesn't click the button, it incorporates that information into its decision next time to show a button to someone with similar features. So it's a little bit how the two are different. And I'm going to start with a really simple example, a relatively simple example. So multi-armed bandits are something that you might be familiar with, and they're actually a simple case of reinforcement learning. And what makes them a simple case is that they're reinforcement learning problems where there's only one state. So what you have is you have a state with particular actions you could take, and these actions are the arms on the multi-armed bandit. So in this case, we have a three-armed bandit. So there's three actions we can take, but they're all from the same state. So I'm in some state, and I can take some action and get some reward. But then after I take that action and get that reward, I can then take some other action from that same state. So really all I have to think about is which action should I take and what is the reward structure? And so remember, we don't have to train the model beforehand. We can just throw it out there with it not knowing anything about these reward structures. And then it will learn as it goes which one it wants to pick. And what it's trying to do is find what's called an optimal policy, which is which action should it take and when for a particular state and environment. And so what we're trying to do here is trying to understand what is this distribution from which these rewards are being sampled. So remember, multi-armed bandits are named after one-armed bandits, which is a colloquialism for slot machines. And they're called one-armed bandits because in the long run, and I hate to burst anybody's bubble, but if you play slot machines long enough, you're going to lose money. So I hope that doesn't ruin anyone's weekend plans. But it turns out that casinos actually win in the long run. So you pull this arm, and in order to keep you there, obviously they're not just going to take your money every time. Some of the time they're going to give you some reward. And those rewards aren't always going to be the same. So you're not always going to hit the jackpot. Sometimes maybe you get 2 sevens and a cherry, and so you get a little bit of a reward. Sometimes maybe you get 3 bars, and you get some other amount of reward. And thinking about the multi-armed bandit, the idea here is that for each arm that you pull, the reward structure is different. And you want to figure out which arm should you be pulling, but you don't have any initial information up front. So you want to know, what is the reward for this particular arm? Or you can think of it as 3 different slot machines. So if you have the option between 3 different slot machines, which one should you be playing? And so you'll want some way of deciding which action should I take. And let's say that you take action 1 and you get reward 1, and let's say that you win a little bit of money. Should you always just keep playing that same slot machine? You might think so because the reward for that is positive and all the other ones are unknown. So maybe you think of them as 0. But really you want to balance this, exploiting the fact that you know that this one pays out and exploring these other ones. That way you minimize regret. The regret that maybe you chose wrong in the future and it produced a lot of wrong consequences. So this is sort of a simple problem, and it's often used in things like conversion funnels or online for things like a type of testing or experimentation online. But then it generalizes into the reinforcement learning problem, which you can really think of, to simplify it, as just this multi-armed bandit problem, where after you take some action and you get some reward, you actually transition to a different state. So thinking of a more complex reinforcement learning problem, let's say that you had a robot who was in a room and their job was to pick up aluminum cans and recycle them. Well, the environment here is this room, and when I pick up an aluminum can to recycle it, actually the state of the room changes. So whereas in the first state, there is this option to pick up this aluminum can and recycle it, after I recycle it, I'm in some new state where this option isn't available. Or maybe I move around the room, so my state changes and the actions available to me are different. And depending on which action I take, the rewards are different. So you can imagine I'm in state 1, I take action 1, now I'm in state 2, maybe I take action 5, now I'm in state 3, and it's added complexity on top of a single state problem. So now how do we model this? So this is sort of the goal of the library, is to model this in a way that's easy for learning and comparing different reinforcement learning algorithms. And you can think of it as really just 2 key components. So it's actually sort of simple to model. So one piece is the agent, and the other piece is the environment. And the agent is just the thing that acts, and the environment is just the thing that you act in. So the agent takes some actions in the environment and gets some rewards. And potentially the environment also changes states. So how do you know which action to pick? Well, there are different methods for picking it, but the context in which we'll talk about it now is a tabular context, where we actually want to keep a record of, for each state and action, the reward values. So you can imagine this table representing, for state 1 and action 1, of all the times that I've taken that action in that state, maybe I'm averaging the reward, and the average reward is 0.2. And then likewise for action 2 in that same state, my average reward is negative 7.9. So if I'm simply just picking the best option and I want to maximize the reward, I'm going to go with action 1. And then what I do with this table is every time I take an action, I get some new reward. And then I incorporate it into the average so that the next time I take an action, I have updated information. And of course, this is really easily represented functionally as just giving me the state and then giving me the action, and then I give you some reward. So let me talk a little bit about how to model this in Scala. So of course, one thing we have is an environment, and the environment is really pretty straightforward. It's just all the possible states and all the possible actions for each of those states. And then of course, because this is immutable, we want the current state that we're in. And then environment has a method on it called act. And when you act in the environment, it returns another environment with the state updated. And then of course, the agent needs to use this environment, and the agent actually has different goals that it could be targeting. So one is a reward, one is a preference right now, but there could be other types of goals. And then it uses the environment to act in. And then there are two key parameters here. So one is the action selector, and this is really maybe the core of the usefulness of the library, because the action selector are really the algorithms for deciding which action to choose. And this is a lot of times what you'll want to be comparing when you're comparing different algorithms for reinforcement learning. So one example of an action selector, and maybe the most popular, is epsilon greedy. And with epsilon greedy, what it does is some percentage of the time, say 90%, it will just always pick the best option. And then say 10% of the time, it will explore randomly all of the other actions. That way it doesn't lose out on a potentially better action, but it also is able to maximize the rewards. But there are other action selectors as well. Another common one is upper confidence bound, where you want to incorporate the uncertainty in your estimate of the reward. So if you have a lot of uncertainty, you might want to keep exploring that until you get enough information to reduce your uncertainty in that estimate. So the nice thing here is that the agent allows you to really easily pass in these algorithms, and there's a bunch already in the library, but you could write your own custom action selector and pass it into the agent very easily. The other piece is the updater. Updater is just another function. And this function is used for updating that table we talked about. So you might just use the sample average, which is just averaging the rewards over all of the times that you've taken that action. But in other cases, you might have like a non-stationary environment where as time goes on, actually the reward structure changes. So if that happens, one thing you might think is that you don't want to weight the rewards that happened a long time ago as much as the ones that happened more recently, because you think the ones that are more recent are going to be more indicative of rewards that you're going to see in the future. So there you might want to use something like an exponential recency weighted average. So these things are available in the library as well, and you can swap them in and out. And then the last piece here is just that table that we talked about, where it's really just a map from state to actions and rewards. So this is sort of very high level, just the interface for the agent and the environment. And to talk about like how you might implement this concretely, Erin's going to talk about a game that she wrote using the reinforcement learning library.
So here's my example of tic-tac-toe. As you probably know, tic-tac-toe is this game where there are two players. One is assigned X, the other is assigned O, and they take turns filling this 3x3 array and attempt to get 3 in a row before the other. So for my example, the UI is implemented in React, and the server is implemented in Akka HTTP, which uses the reinforcement learning library. So the environment the computer is navigating is this tic-tac-toe board, and the environment is holding all the states that the computer could possibly encounter, as well as all the actions that the computer can take from those states. So for winning state values, the state values are equal to 1, and the losses and draws states are equal to 0, and all other state values start off as 0.5 and are updated as the computer plays and learns. So the way that the computer chooses its actions is by exploiting the state with the highest value 90% of the time, and 10% of the time exploring, randomly selecting different actions. And to update the states, when the computer exploits 0.9 of the state that it exploited to will go back and average out with the previous state, and that will update the previous state value. When the computer explores, however, the previous state value isn't updated at all. So, like I said, the environment is holding these possible states as well as the possible state actions. And the way we're generating these states is we're giving this function an empty array, and the function is alternating, putting x's and no's onto the array, also with some blanks, in order to make possible states. And the reason it's alternating is so that it doesn't make any impossible states that the computer will never encounter, such as a board full of x's, which just isn't possible. So here is where here's where the computer is being told what the computer can do in those states, where the computer can place its O. And here is where the state values are initially being given. All the winning states are being given a value of 1. All the losses and draws are being given a value of 0. And all other values are starting as 0.5. So here's the computer. The computer is using epsilon greedy, which is when it 90% of the time exploits the highest state value and 10% of the time explores. And it's also using temporal difference learning method, where it gives 0.9 of the state that it exploited to back to the previous state and averages out with the previous state's value. So here's an example of the tic-tac-toe computer actually playing. So the computer is playing against a player that's imperfect, that doesn't immediately get those wins as fast as maybe 2 players who experienced are playing, just to give the computer an opportunity to update its state values and see how it can win, how it loses. So as the player and the computer are playing, the player is going to those same values, and when the computer loses, those state values are decreasing, and so the computer, when it's exploiting, won't go there. And when it finds a way to win, those state values are increasing. So when the computer exploits 90% of the time, the computer will continue to go there. And if it's not going there, it's exploring the other 10% of the time. So now to talk about Scala 3's features. Okay.
Cool. So that's a nice example of how, with actually very minimal code, you can write a nice implementation of a reinforcement learning application. And in this case, it's tic-tac-toe. So you have this sort of framework available where you can just write the things that are specific to the tic-tac-toe game. And one thing that you could, very easily do here is, swap out different algorithms to see which ones perform better. So why Scala 3? One thing you might ask just in general is why Scala? So a lot of reinforcement learning code that you see is actually written in Python. And in fact, one of the things that is in the repo with this library is a lot of examples from the Bartow and Sutton book, which if you look for examples of that code, it's pretty much all in Python. So you might just wonder why Scala at all? Why not Python? And one answer is maybe if you've ever used Python, then the answer is immediately obvious. So Scala, I think, is preferable for a lot of reasons. So if you look at some of the code, one thing that's not as easy to do in Python is to model something in a way that's easy to understand and use. And part of that is maybe just sort of idiomatic Python. So if you look at, or sort of self-taught Python engineers, so if you look at a lot of the examples, a lot of the code is rewritten over and over again for different chapters of the Bartow and Sutton book. And what that means is that it's hard to compare what the changes are. So like if we're learning about temporal difference in one chapter and we're learning about bandits in the other, what is that connection? So if we model that really well, which is a lot easier in Scala, then it's a lot easier to learn about reinforcement learning and understand what the differences are in these different methodologies. But specifically, why Scala 3? So I have a few of the reasons here, but I think by and far opaque types is probably the #1 reason. So I've always been a fan of value types, but we know how dangerous those are. And the nice thing about opaque types, especially for a library like this, is that a lot of times, and just to say what opaque types are, opaque types are like value types in that they're types who at compile time are just primitive types. So you don't have the overhead of types, but you have the type safety that comes along with typing something. And in a reinforcement learning library, you have these different things that are all doubles. You have rewards, you have preferences, you have probabilities, and it's really important that you differentiate these and that you're passing the right thing to each method. But it's also important because you'll often have tens of thousands or hundreds of thousands of these in memory that they're efficient. And so opaque types is a really huge benefit with not having to worry about boxing and unboxing happening when you don't expect it to. Compilation speed, I mean, especially when Dottie was first coming out, was a big deal. And it's still a big deal for reinforcement learning because oftentimes what you're doing is, you're iterating on these algorithms. And you want to compare these algorithms, and comparing these algorithms often involves simulations of you might do 100 simulations and each one has 1,000 steps. So, you have the compile time plus the runtime, and you really want to make sure that the compile time is really low because the runtime is already going to be pretty costly. So just to give an example of an opaque type, this is actually a really simple example. One of the things that we track in the reinforcement learning library is how many times you've taken a particular action. So this helps with doing things like averaging out over all of these actions. And you want a step to be able to increment, but you also want it to be low overhead. This is just an example to show how opaque types are structured. Really a better example in the library is probably the probability opaque type, where it has a lot of methods on it that allow you to do operations that you would expect to be able to do on probabilities, like multiplying probabilities or adding them or something like that. So union types are really nice for a couple of reasons. One is when you think about opaque types, one of the things about opaque types is they can't inherit from other types, or they can't inherit a trait or extend a trait. So union types are a nice way to be able to have a single type that, let's say, your class can use. In this case, it's a goal, and those types in the union are actually opaque types. Union types are actually nice for some other reasons. So, in Scala 2, I used a lot of sealed traits with, case objects to do things like enumerations or union types. And I think one of the things that, as I iterate on this library more, is I'll probably start using union types in a lot of those places where I use sealed traits. It's just sort of a habit that I have from Scala 2. But it's a really nice feature. Trait parameters are nice. So, I mean, the nice thing I like about trait parameters is that, typically I just want to use traits. I very rarely want to use abstract classes. And I would often have to switch to an abstract class just because I wanted the class to have, or the trait to have parameters. And not having to make that switch and use traits exactly when I want to is a really nice feature. There's a lot of nice syntax features that are really helpful. I mean, remember that this is for learning and comparing algorithms, this library. And so really what you want is as simple of syntax as possible. So this is just showing off parameter untupling. So normally we would have like a case here, and that can be a little bit confusing for people who aren't familiar with Scala because it looks like you're only handling one case. And in fact, you kind of are, but with parameter untupling, it's a little bit clearer what the function is doing without the extra verbosity. And you might think, oh, this is a small change, but you really want your code to be as simple as possible, especially for something like reinforcement learning, because you really want people to be able to onboard to your library very easily and be able to implement new things very easily and compare them with as little fluff as possible. And another way to think about this is when you're modeling things, what you really want to do is you want to model the thing in the world the way that you want to. you don't want to have to think, I have this model for the thing that I'm modeling. How do I implement it in this particular language? Ideally, the model that you express in the language that you're using is really a really good representation of the model that you have in your head. And so a lot of these syntax improvements really help get there with Scala 3. And you'll see in the library, there are other things like sometimes I use if, then instead of the parentheses and the curly braces when it's appropriate. And it really just helps with the readability and the flow of the code. Cool. So I'll talk a little bit about next steps. So the library is in GitHub, and it has a lot of algorithms available and some documentation, but there's some more documentation that needs to be added. The other thing is right now it's only supporting these tables that we talked about, where you store the reward values in these tables. But in a lot of cases in reinforcement learning, you have so many states, or you might even have a continuous state space. So storing all of these states in a table is really not possible. So there's function approximation is a way of handling that, and that's something that I'll be implementing in the library shortly. There's a few chapters from the Bartow and Sutton book in the repository, which helps with learning. We'll be adding more of those chapters, iterating more on the model representation. So, as I add function approximation, these other things, really getting the interface of the model right is going to be important. And so you might see some iterations on that. And then, as I mentioned, there's a lot of new Scala 3 features that I'm still getting used to. I have some old habits from Scala 2. So I'll be incorporating more of the Scala 3 features into the library as well. Cool. So like I mentioned, I'm a software engineer at Twitter. Our team is hiring. I'm on the experimentation team. So if you're interested, check out the Twitter careers page. You can find me on Twitter at Robert J. Neal. My GitHub is github.com/RobertJNeal. Big thanks to Aaron for showing off an implementation of this. I think it was really helpful. There are a couple of references for reinforcement learning. The Bartow and Sutton book that I've mentioned quite a few times is really good. There's also a really good YouTube series by David Silver on reinforcement learning. And I was going to add some Scala 3 resources on here, but presumably you guys are all familiar with those. The Dottie help pages, I think, have been the biggest resource for me, but there's also a lot of good resources out there on the web. Cool. And that's all I got. Thanks.